remember, before break, we looked at simplifying and proving with our trig identities. So we're still looking at trig stuff, but now we're actually looking at numbers. Who would have thought? We're going to bring the numbers back in. Okay, so let's think back to when we did like solving systems of equations. What's the first method that we look at? Graphing. So we do graphing. That's why don't forget about it, because you don't use it very often. Yeah. So we're going to look at graphing first for solving a trig equation. However, it's going to be the same type of thing. We're not going to use it quite as often, but it is kind of a good place to start. Yes? So again, thinking back to systems of equations, when we're solving systems of equations, what are we looking at before to find our answer? How do we know where our answer is on the graph? Where the lines meet, and what's that called?
One supertext.
Not quite. It's a what of intersection? A point. It's a point of intersection. Okay? And it's going to be the same thing here. So hopefully we notice and remember that this is our sine graph. Okay, this is your sine equals x. So remember our sine of x starts at 0, 0. You go one full rotation to 2 pi. 2 pi, which is also a 0. Halfway in between is pi, which is also a 0. And then halfway in between at pi over 2 is our maximum at 1. And at 3 pi over 2 is our minimum at negative 1. Okay? And that gives us the left side of this equation. So basically what we're trying to say is what x value or what angle for sine of x gives us 1/2. So the same type of idea, I've graphed sine of x. If I graph 1/2, that's going to be a horizontal line at 1/2, which is what this like pink dotted line is. And we're looking for the points of intersections between those two things. Y'all with me? Okay? Because again, we're trying to figure out what x values make this statement true. So kind of like when we did our inverse trig functions, we're saying what angle, if we plug it in for sine, gives us 1/2. Or on our graph, where are we going to equal 1/2? So what's our first point that they've labeled here? Pi over. Okay? Which makes sense because we're positive for sine in our first quadrant and we're above the x-axis on our graph. Now where's the second spot that they have labeled? 5 pi over 6. Now, does our sine graph just stop at 2 pi? No, right? That's one full rotation or one full period, but it goes on forever, right? So how many solutions are we going to have? An infinite number of solutions, right? So if I ask you to solve sine of x equals 1/2, you don't want to sit there all day long writing out every single solution, right? So it's helpful if we kind of have a shorthand, which is going to be how we write our general solutions. So if I just ask you to solve between 0 to 2 pi, then these would be your solutions. You would get those. However, if I ask you to solve for all solutions, we have to consider that I get more solutions than that. Okay? But notice, how do they label my next solution? Pi over 6 plus 2 pi. Well, why did they choose pi over 6 plus 2 pi? Yeah, it's going to be the same angle because it's going to have the same remember our values repeat themselves every 2 pi, which is also why they have minus pi over 6 plus 2 pi. And remember that we can add 2 pi as many times as we want. And then going to the left, notice that they subtract 2 pi to get those answers. So we have pi over 6 plus 2 pi. But how could I make it to where I can add or subtract as many 2 pi's as we needed? So there I added 1 2 pi. Then I could add 2 2 pi's. Then 3 2 pi's.
Times the number of beans.
Correct. Okay, now how could we represent that?
The variable.
With a variable, I agree. And the specific variable that we use most of the time is going to be n. And n is going to be an integer. Now remind me what type of numbers are integers. Whole numbers, or are they just positive?
No,
Negative and 0. Because notice if I plug 0 in for n, I just get my first two to be pi over 6 and 5 pi over 6. If I plug in my negatives, that's what's going to give me those backwards or to the left solutions. And then if I plug in 1 through infinity, those are going to give me all of my other solutions. Are y'all with me on that? Now, I wrote where n is an integer on this answer because it was the first time we were writing it. In the future, you don't have to write that statement. You just have to do pi over 6 plus 2 and pi. And because it's common notation, it's understood that n is an integer. So you don't have to write out the where n is an integer every single time. Mathematicians are lazy, and we don't like to write that much. So. Questions on any of that? No? Okay, so like I said, for the most part, we're not going to graph things to specifically solve them. However, sometimes I might refer back to the graph or have us think about the graph in order to help us solve. So that's why I wanted us to talk about what it looks like to look at a graph. And then there could also be situations where whatever's on the right-hand side is complicated enough that we don't want to try and solve it algebraically. So then you would just graph the left hand and the right-hand side and see where they intersect on like a graphing calculator or decimal. And I think there is one like that in your homework, so you'll just plug both of them in and then figure out where they intersect. So that's all it's asking for you. But for the most part, we will be using algebraic techniques. And what I mean by that is just all the stuff we've used to solve before now. Meaning like our opposite operations, so adding, subtracting, multiplying, dividing, taking the square roots of things, squaring things, all of those stuff still apply. Sometimes we might have to combine like terms. Sometimes we might have to factor it. Right? All of the algebra stuff that we have learned up until this point is still valid. Right? So I think that's usually where the hard part is for some of these types of problems is because students get so focused on the like trig stuff that you forget about all of your algebra stuff. So that's usually where people make the most mistakes, is just the algebra part. Okay? But our goal is going to be to isolate the trig function. Right? So just like if I had, say, 2 square roots of x equals 8, right? Well, I know that squaring both sides undoes my square root, but I can't square both sides until my square root is by itself. And then we're allowed to square both sides. So we need to do the same thing with our trig functions. My trig function has to be isolated or by itself before we can attempt to solve it. Questions on that? Okay, let's look at an example. So here we have a cosine. We have 2 cosine minus the square root of 3 equals 0. Again, we're trying to figure out what x values make that statement true. It just happens to be because we have a cosine, we're specifically dealing with angles instead of just kind of numbers. So what did we say our goal is? Isolate the trig function. Is my trig function isolated or not? No. I have a square root of 3 and a 2. But again, let's think back to our just normal operation. If I have a minus square root of 3, how do we undo that?
You add square root and zero.
Agreed. So we're going to add square root of 3 to both sides. So then we have a times 2 on the outside. So how do we undo multiplying by 2? Divide by 2. So we end up with cosine of x equals the square root of 3 over 2. Now hopefully that looks vaguely familiar, right? Because what's the magic tool that Mrs. Bennett told you that you were going to have to know for the remainder of the semester, because it was going to come up all the same time. The unit circle. Okay? So, square root of 3 over 2 is on our unit circle. So we can basically work our way backwards. You can think what x value or what angle for cosine gives us square root of 3 over 2.
I over 3, 6.
Okay, and then what did we say we need to add?
2 and
Yep. Now, this is my first solution. Okay, so that happens in my first quadrant. But is there another place on my coordinate plane that cosine is also positive?
Let's see. Quadrant 4.
Yes, so my fourth quadrant. So we need to find the angle in my fourth quadrant that has a reference angle of pi over 6. 11 pi over 6. Now, so far, we're doing these in radians, just because I'll need more practice with radians. These could be in degrees as well, okay? And we would just write 30 degrees, right? And so forth. But then instead of putting 30 degrees plus 2 and pi, what would I put? 30 degrees plus 360 times n. So same type of idea, just using degrees. And sometimes you'll see problems written in either one. That's fine. I'm probably going to focus more on the radians, just because you all tend to struggle a little bit more with the radians. And remember that our radians are a pure unit, so a lot of times we don't want the degree unit on there when we're trying to solve a real-world application. So far, so good? Questions on that? Alright, I want you to try the next one on our own. Same type of idea. Alright, so hopefully all of us were able to at least isolate this sine. At least that's what it looks like. Most of us didn't have any problems with that. It's pretty straightforward. I get negative 4, and then I divide by 8, and we get a negative 1/2. Now, a lot of you automatically kind of referred back to our unit circle, and that's fine, okay? But remember I said sometimes it might be a little bit easier to refer back to our graph, right? So remember our sine graph, so I know that when x equals pi over 6, sine is at a positive 1/2, which means that if we go the opposite direction, this would be at a negative pi over 6 when it's at negative 1/2. Yes? So what angle is going to be equivalent, or the coterminal angle, for negative pi over 6? Agreed. Because we would be going clockwise, right? And so we would be in our fourth quadrant, so we get 11 pi over 6. And again, we need that plus 2 in pi. So then what other quadrant are we going to be in? So we had 1 in our fourth, we'll also have 1 in our third, but it has to have the same reference angle, which is going to be pi over 6. So what angle in our third quadrant has a reference angle of pi over 6? 7 pi over 6. Question on that. No? Question? No? You sure? Are we stuck on the part? Okay. Let's look at another one. So, what's different about this one? It's tangent. But it's still a trig function, right? So my steps are still going to be the same to isolate. The only difference is when we actually start trying to figure out what x values make our tangent true, that part's going to be a little bit different. But in order to isolate, what's going to be our first step? Which gives us 3. And then if we divide by 3, we get 1. Yeah? So remind me, what does our tangent graph look like? So it kind of looks like our cubic graph, right? Like that. And then what's special about our tangent graph? What does it have? Yeah, it has asymptotes. Okay? Now remember, specifically our asymptotes happen at negative pi over 2 and pi over 2. Okay? And remember that we also have key points at negative 1 and 1. And the nice thing is that this is exactly halfway in between 0 and pi over 2. So at what value, what x value, does it equal 1? Pi over 4. Right? We all see kind of how to work our way backwards. Now, the other way that we can think about this is that we know tangent of x equals sine over cosine. So in order for tangent to be 1, we know that sine has to equal cosine. And remember that the only place that this difference is at pi over 4 because sine of x and cosine of x are both square root of 2. Yeah, with me? So either way, you want to think about it using your graph, that's fine. You can also think about it using sines and cosines and our unit circle again, and knowing that sine and cosine have to be equal, which happens at pi over 4. Now, what do we need to add to our answer? Be careful. What's the special thing about tangent and cotangent? Yeah. They have a period of just pi instead of 2 pi. So this time we're going to add in pi instead of 2 in pi. So technically, it would also be a positive 1 in our third quadrant as well, which would give us 5 pi over 4. But because our period is in pi, this first one takes care of this next one. Because if I plug in a 1, right, pi over 4 plus pi is going to give us 5 pi over 4. So really, the only thing that we need to write for our answer is going to be this first one. Now, if it makes you feel better, or you prefer to write out both of them, that's completely fine. And I'm not going to count it wrong for writing out the second one, but just realize when you're checking your answers in the back of the book, it's only going to list this first one because that takes care of both of these. Now, if I said solve this equation between 0 to 2 pi, then you would have to list out pi over 4 and 5 pi. Because both of those are valid. Questions on that? So, we said for tangent and then also for cotangent, we would add in pi. So that means, what would we add for secant and cosecant? We would still add the 2 in pi. Because remember, those are our reciprocals for sine and cosine. So they have the same period for sine and cosine. The only time that your period is going to change and not be 2 pi or pi is if we start to have stuff on the inside of our functions. Like if I had tangent of 2x instead. And we'll look at some examples of those on Wednesday, but we're not quite there yet. Alrighty, what's different about this one? There's 2 trig functions, but are they the same trig function? Yes. Well, they're both sines, yes. So it's kind of like if I had x's on both sides of an equation, what do I do to them? Not cancel them. Not necessarily. It depends. Where do we want them? Right now, those are on opposite sides. Yeah, we want to move them all to the same side. Yes. So it's going to be whatever operation we end up needing to use. So sometimes we might add, sometimes we might subtract. In this case, I'm going to add the sine x on the right to both sides. Because just like with our normal x's, usually it's just kind of helpful to have things that are positive. So this allows us to have a positive 2 sine of x instead of a negative. Now, if you got a negative trig function, you just divide by a negative at the end. But we don't have to worry about that if we go ahead and keep it all positive. So now this looks very similar to what we've been doing. So what do I need to do in order to isolate my sine of x? And? Side 2. So we get sine of x equals negative square root of 2 over 2. So where does sine of x equal positive square root of 2 over 2? Pi over 4. But we need the negative one this time. So we know that we're going to have a reference angle of pi over 4. But we know that we need to be in our third and fourth quadrant. So what angle in our third quadrant is a reference angle of pi over 4? And in our fourth quadrant? And again, because we have sine this time, we're going to add the 2 in pi. Questions on that? Yes? Hey, he's got a couple more things.
Are you going to be working on the inverse of this? Right? Again, first we can see.
Like with trig equations, most of the time you don't get equations that have inverse trig functions. You have to use your inverse trig functions to solve equations, but you won't get most of the time. Unless you have some super funky equation, you're not going to be given something that has an inverse trig function. Alright, what's different about this one?
It's what?
It's squared, okay. Now, how do we undo something being squared? We square root it. So same thing. Our normal algebra stuff still applies. So we're still going to use those same steps. But remember, I can't square root something until whatever's being squared is by itself. So what do we need to do here first? Agreed. And then, when we take the square root, I get the square root of 1/3. Okay. But if I have the square root of a fraction, we can take them separately, and so what do we end up with? We could, I'm going to go ahead and leave it like this. Because remember that this isn't my final answer. So remember, if it is my final answer, I need to rationalize. But in this case, it's actually going to be a little bit hopeful for us to not do that yet. Am I missing anything? Before I start solving for x. It is. So remember that when we take the square roots, we have to add a plus or a minus. We're actually going to get double the answers this time. Okay? Now, the easiest way to think about this, so again, remember that tangent of x equals sine of x over cosine of x. And remember that your three options on our unit circles for our values are square root of 2 over 2, square root of 3 over 2, and 1/2. Well, remember that if sine and cosine, or if either one of them is square root of 2 over 2, the other one has to be as well. And so that would give us 1. So we know that our other two options are going to be the square root of 3 over 2 and 1/2. And whichever one is 1/2 and which one is square root of 3 over 2 is going to determine if we're at 30 degrees or if we're at 60 degrees. Does that kind of make sense? Now, the reason that I said that we want to leave this unrationalized is because notice that my square root of 3 is in my denominator, which means that my square root of 3 over 2 also has to be in my denominator, which means that I know my tangent is the one that has to end up having the square root of 3. We all see how it kind of like works my way backwards there? Yes. square root of 3 over 2? Is it our 30 degrees or our 60 degrees? It's your 30, which in radians is pi over 6. Now, remember with our tangent, it's going to be positive in our first and in our third, but because I added in pi, that takes care of both of those. Alright? However, we also have a negative, so that means we also need to look at our second quadrant. So, if we want our second quadrant, but we still want a reference angle of pi over 6, what would the angle be? So in our second quadrant, we're thinking what angle has a reference angle of pi over 6? Because in our second quadrant, tangent is going to be negative, but if it has a reference angle of pi over 6, I'm going to get the same value of 1 divided by the square root of 3. The only thing is that's going to change is now it's going to be negative, which is what we want. And again, it would also be negative in our fourth quadrant, but because we add the in pi, that answer takes care of our fourth quadrant.
I have a question.
Sure.
If we were looking for sine of x instead of cosine of x, would the reference angle be any different?
You mean like if my answer was just the square root of 3 instead? So then my sine is what would be square root of 3?
Yeah.
Yes, because sine is going to be square root of 3 over 2 at 60 degrees, which is pi over 3.
Okay.
So that's why it depends on if your square root of 3 is in the top or the bottom on which one you're looking at. If it's in the bottom, cosine is square root of 3 over 2, which means that I'm looking at 30 degrees. If it's in the top, that means that sine is square root of 3 over 2, which happens at 60 degrees.
Ah, so you would still reflect the reverse in axis.
Yeah, you would still like find your reference angles the same. I would still be looking at my second quadrant. I would just be using reference angles of pi's over 3's instead of pi's over 6's. But yeah, those quadrants of when they're positive or negative are always the same. So we can always use that same process, just whichever reference angle you would use. Good question. Other question? Alright, I think we have time for one last example. What's different about this one? There's more than 2, yeah, we have 3 this time, but also they're not the same one, right? In our last one, they're both sides. Here we have 2 different ones, okay? But let's use kind of that same idea. When we had trig functions on both sides, what did we do?
We put same trig functions on one side.
Yeah.
So we would probably just switch them around so that cotangent's on one side and cosine on the other.
We can't quite do that, but I do agree with the first statement. We want to put everything, or we want to put our cotangents on the same side. So in this case, I would subtract that cotangent. The only problem is because my cosine squared is being multiplied by the cotangent, I can't move it over.
Divide both sides by cotangent.
We can't quite do that because if we divide both sides by cotangent, right? In most cases, that would be fine. But what's the one time that we're not allowed to divide things? Like the world explodes when we divide. When we divide by 0, right? And we have points, right, at which cotangent is 0. So because there are spots or there are times when cotangent could be 0, we can't divide by it. because then that would be divided by 0.
Oh, yeah.
Does that make sense?
Mhm.
But I'm liking the idea. Is there something that's similar to dividing, but that isn't quite dividing? Yeah, factoring. So same idea. We're trying to move that cotangent away or get rid of that cotangent. We just want to factor it instead. So if I factor out a cotangent, what do we end up with on the inside? Okay. Now think back to like your quadratics. Once I have something factored,
So,
yeah, so like with our quadratics, we set each of our factors equal to 0. Here, just because our factors happen to have trig functions, that doesn't change anything. I'm still going to set each of them equal to 0. Well, it's kind of nice on our first one. Our trig function's already isolated. So how would I isolate my cosine on my second one? Add 2 and then take the square root, but what do we have to add? Plus or minus. Good? And then basically we're just going to solve. So remember that cotangent is the opposite. So it's cosine over sine. Alright? And think, in order for something to equal 0, which one, my numerator or my denominator, has to be 0? Well, what did we just say we're not allowed to have equal 0? We're not allowed to divide by 0. So we know that our sine can't be the one with 0. It's going to have to be our cosine that's 0 instead. Because 0 divided by anything is still going to give us 0. Okay? So when does cosine equal 0? And 3 pi. Yeah. So pi over 2 and 3 pi over 2, but because we're adding the in pi, that takes care of all of them. Okay. Now, is the square root of 2, so we need to solve our second equation now, is just the square root of 2 on our unit circle. Is it one of our values that we said that we can choose from? No, right? We have square root of 2 over 2, but not just the square root of 2. So when we have something that's not on our unit circle, how do we get rid of or undo the cosine? Or what's the opposite of a cosine? Talked about it in that's the reciprocal,
Oh,
but those don't undo each other.
negative cosine.
Almost. Nope. Negative sigma? Nope. What undoes cosine if I take it to both sides? Cosine inverse. Because remember that because they're inverses, they undo each other, and we would just be left with an x. Now we would just plug that into our calculator. But if you plug that into your calculator, you would actually get an error. And we will tell you why.
Because it's plus minus.
Not because it's plus minus. You would do cosine inverse of square root of 2 and then cosine inverse of negative square root of 2. You would get two answers. But either one of them are going to give you an answer. What is square root of 2 equal? A background
1.4.
stuff, right? Well, let's think about our y value for our cosine graph. What do they have to be between? Well, where's our maximum and min?
Oh, 1, 0.
1 and negative 1, right? So that means that our stuff on the right-hand side also has to be between 1 and negative 1. Square root of 2 is outside of that, so we don't get an answer for that. So that means that our only answer would be that one right